as a next presentation, we will have Andreas Rennings from the University of Duisburg-Essen, and he gives a talk about dipole simulation. So it's your turn.
Thank you. Yeah, good afternoon, everybody, and welcome to my talk. First of all, I would like to thank Tim for inviting us. My talk is about a project we had. Mr. Chen was a PhD student. He did mainly the work, and Professor Solbach and me were the PIs of this project. It's about RF dipole coils, and we took that one and placed a so-called high-impedance-surface shield behind that dipole to increase its properties. Here's the outline of my talk. I will start with a quick introduction and mention our objective. Then I will go over to the numerical simulation of the His structure. Then I will come to the full wave simulation of the dipole coil, including this His shield. And finally, I would like to show an array of these dipoles. In the end, I will conclude my talk. Here's the introduction and the objective of this project. We would like to use this high impedance surface, and another term more widely and well-known term would be an electromagnetic bandgap structure. This periodic surface has two properties. One would be the high impedance surface, and the other one would be a forbidden frequency bandgap where you don't have electromagnetic surface. As I mentioned, it exhibits an in-phase reflection coefficient for normally incident plane wave at a certain frequency that would correspond with the resonance frequency of this artificial surface. And here, that was the other property. It prevents the propagation of the surface wave at a certain frequency. So we get two properties depending on the way you interact with an electromagnetic wave. In the first case, you normally you have a normal incidence, and in the second case, you have a parallel propagation along that surface. And the characterization of the surface is based on the so-called reflection phase, and the other one would be the dispersion diagram. And here you have considerations of this His design for the MRI application. One thing is important, the lattice dimension, so the unit cell of this periodic structure must be a lot smaller than dimension of the RF coil in order that you get an artificial homogeneous surface behavior. There are at least two typical His designs out there. One is called the uniplanar one, and I will focus on that one, and the other more original one is the so-called mushroom-like topology. And if the unit cell is getting too large, you get some parasitic effects. We will see that later on in the talk. The objective of this DFG project was to investigate the feasibility of this high impedance surface as a shield behind a dipole coil and also behind a loop coil to improve the homogeneity, the B1 homogeneity, and also the penetration depth. So here in the lower left, you see the topology of the unit cell of this high impedance surface. It includes a 3 metal layer. Here the lower one would be the backside ground plane. Then we have here in red floating metal layers, and here the top metal layer in black. The high impedance comes from a parallel circuit where you have here the conducting line that would be an inductor, and in parallel you have this capacitor here constructed from this MIM capacitor in series with another MIM capacitor. So at the resonance frequency, at the resonance between this inductor here and this capacitor here, we have the high impedance behavior. And this high impedance behavior more or less mimics a perfect magnetic conductor. When we place a perfect magnetic conductor behind, for example, a dipole coil, we, instead of having an out-of-phase image current, we have an in-phase image current. And that makes the B1 field larger. So that's the general idea behind the usage of this high impedance surface sheet. And such a high impedance surface, or in other words, such a perfect magnetic conductor, has a reflection coefficient of +1, and that corresponds to an in-phase reflection coefficient. So here at the operation frequency, we get really a 0-phase reflection coefficient. For a pack plate, so for a good metal conductor, we would have 180 degrees. So there, the reflection coefficient would be -1. Here we have +1. As you can imagine, you don't get that in-phase reflection coefficient for in a broad range of frequencies. It's frequency dependent. And here in these two plots, we see the frequency dependence of the reflection phase, of the reflection coefficient, in other words. For low frequencies, it's 180 degrees. So then for low frequencies, we really see the backside ground plane. So the field penetrates through the structured metal here, and then we see that guy. And for very high frequencies, the capacitors here are short-circuited in an RF manner. And again, we have a PEG behavior. But in between, at this frequency here, we have a 0 reflection phase, and that's really what we want to have. Here we checked out the dependence of the reflection phase on this incident angle here. In HFSS, there is a special GUI or a special setting where we can nicely extract that information. We excite a parallel plane wave. In this case, we have the TE polarization, where the electric field remains parallel to the surface. And when we increase this incident angle here, the H field is getting more and more a normal component. And that is here the results. So you see the resonance frequency is not changed. What is changed is, let's say, the Q factor of this resonator here. When you increase the angle, the function is getting steeper and steeper. For the TM case, it's the opposite. Then you have the magnetic field aligned here in Y direction, so parallel to the surface. And then the electric field is tilted a little bit. And here you get a slight dependence in terms of frequency. That is actually due to the fact that, let's say it that way, the capacitor is not fully used because the tangential E field component is getting weaker and weaker. So the effective capacitor is decreased. But for the dipole, I guess this polarization here is more important, where you have this E field along the dipole and this H field tangential to the dipole. Yeah, that was the reflection coefficient. And now we come to the so-called dispersion diagram, another way of seeing this periodic structure. Here in this case, it's eigenmode simulation, and here on top we have this PML boundary, so an absorbing boundary, and in X and Y we have what is called periodic boundary conditions, so master-slave condition it's called in HFSS. And there, as I said, it's an eigenmode simulation. There we specify the phase shift from that boundary to that one here, and from this one to this one. And then we let HFSS calculate the corresponding resonance frequency. So we specify here the phase shift along this cell. We may do it in a 2D manner for all values in that direction and in that direction, but this is highly redundant. We just calculate the resonance frequency inside this Brillouin zone. Here, when we go along that direction, we start at the phase origin, that would be here, the so-called gamma point. Then we increase the phase shift in X direction. Then we go along that point here. Then we go on from X to M. We go that direction, and then back to the phase origin. And within this dispersion diagram, all the information is included. As I mentioned, the phase shift is given, and the resonance frequency is calculated. So that would be the eigen frequency of the corresponding eigenmode. And here you can see essentially two modes, the blue one and the red one. The blue one starts here already for very low frequencies. It's a TM-like mode. It's mainly concentrated here in the dielectric. You can see it here. You have straight lines. That would be here the so-called light line, where you have this relationship here. Omega is equal to beta times the speed of light in free space. And then you have another straight line that would be the light line in the corresponding dielectric. It's tilted a little. And here this first mode follows initially that light line of the dielectric, because the field is really concentrated here in the dielectric. But then it goes away, and the resonance frequency is not increasing anymore. Then there is another mode, a TE-like mode. That one is actually concentrated here within these two plates or in the area above the high impedance surface. And there is an area where you have no allowed mode. So no eigenmode is within this grayly shaded area. That is the so-called forbidden frequency band. And that's why we call this structure also an electromagnetic band gap structure. This here would be the band gap. In that frequency range, you don't see any surface wave traveling along that surface. It's actually blocked. And the corresponding frequency where we had this in-phase reflection, that's actually here at the frequency where this TE mode merges the light line. So that would be kind of the correlation between in-phase reflection and the stop band property. So there is some relation, but depending on the structure you are looking at, this frequency might be at the center, somewhere in the band gap, in special cases also outside of this band gap. So it seems there is no direct relation, let's say it that way, between the in-phase reflection frequency point, let's say it that way, and the stopper. But we are still working on that and trying to find something. Yeah, here we use that high impedance surface. You can see it has finite widths. We use several cells in that direction, several cells in the x direction. That you know, it works like a nice sheet behind this dipole coil. Here you can see the cross-sectional view. On top we have the cubicle-shaped phantom. We have a fixed distance of 2 centimeters to the dipole, and then we have a variable distance d to the shield that is behind the dipole. And we consider 3 cases. The case 1 would be the case that this metal plate is a PEC plate. Second case would be the His structure, so the real high impedance surface with the finite unit cell size. And the third case would be a perfect magnetic conductor that you cannot buy. It's a pity, but in simulations we can just say, let the H field be normal. So we just set the tangential H field to be 0. Concerning the dipole, we took the structure on the top layer from the Essen group design, you know, with the straight dipole and the meander at the end, but we removed the end capacitor that was used here between the end of the meander and the backside ground, because when we have the His in the end, we cannot really connect the end capacitor somewhere because it should be an open circuit, a high impedance. Final comment, we added here around the meander a high dielectric substrate to fine-tune this electrical length a little bit, to fine-tune the current distribution along that dial. So it's essentially an ordinary dipole, but the section where you have the low current, you know, where it's going down to 0, that section is meandered because it's not really useful in the MRI context. There we need the strong and quiet current X-directed current. And now in the next slide, we check out the B1 plus or the B1 magnitude in this transverse cut plane. You can see the result. First row would be D, that is the distance from the dipole to the sheet. We increased it from 5 to 10 to 20 millimeter. And in the first column, you have the PEC case, middle current His case, and third column, you see the PMC case. So here, left and right, the ideal cases, and in the center, the His realization. So the His really wants to mimic the PMC behavior. That is the goal. And as you probably know, when you plot these B1 distributions, it's really about the normalization. Here we choose the SAR max value inside this plane in the phantom and took the square root of that value, a local SAR value, to normalize the B1 field. Because at least for 7 Tesla, the local SAR is really the limiting value when it comes to the allowed power that we can apply to the coils. Yeah, and what is visible here in these 9 pictures, that the width of this high field, high B1 field, is smaller here for the PEC case compared to the PMC case, because the magnetic field in the PEC case must go between the dipole and the PEC shield, and in the PMC case, here, it can end in a normal manner on that shield. So the area with high B1 plus is broadened. You can see that width here is more narrow than that one. And except this very close value here, when we compare his and PMC, we see a quite good agreement. So first of all, the field is broadened, as I mentioned, and second of all, the penetration depth is also getting a little bit larger. So here it stops here it goes up to that point, and the value is quite similar. Here in the first row, we see an effect that comes from the finite size of the unit cell. Here we are simply too close to that artificial surface. There it doesn't mimic the ideal PMC. It's kind of different. The distribution itself doesn't look so bad. It's broadened, and the penetration depth is also better than in the PEC case, but we definitely see a difference between perfect homogeneous PMC and finite unit cell size HIS. Here I show you an experimental verification, a validation. In the left column, you see some parts of our near-field measurement setup. In our lab, currently we can measure multi-channel coils. So we have 8 individual channels that can be tuned in terms of magnitude and phase. And we can measure electric and magnetic fields by using these field probes from SPEAG. Here, that's the interface to this optical signal here, and it's connected to a 3-axis positioner. And we use that guy to move this probe within our phantom. Here you may see this fish tank here. It's an aquarium filled with tissue simulating liquid. And by using that one, we can really measure the electric and magnetic field distributions inside the phantom. Here in the lower left, you can see the arrangement. That would be the back side of the shielding plate. That's essentially the ground plane. That would be here the top side, where we can see the unit cells. On top of that one, we have here the dipole aligned in that direction. We use a balloon here, a transmission line-based balloon, to feed that balanced antenna. And we move the probe here along this XZ transverse cut. And here you can see the corresponding result. The normalization has been done in an equal manner. We normalize everything on the local SAR max. And we definitely see that for the PEC case, the distribution is more narrow compared to the HIS case. The PMC case is not available because we cannot buy such a shield. And also the penetration depth is a little bit larger. It's tricky to see. The difference is not really huge. In the next slide, where I talk about the multi-channel arrangement, the difference is more obvious. Here is the multi-channel simulation. I'm talking about an 8-channel arrangement, similar dipole coil. The interesting thing here is really that we did this simulation in OpenEMS. Why? Because it offers the cylindrical FDTD mesh. The tricky point is really this extremely thin, high dielectric between the top layer of the HIS and the red intermediate floating layer of this high impedance surface. We use this extremely thin layer to get a large capacitance to decrease the resonance frequency as much as possible. And that thin structure here really makes numerical simulation not easy. Even in Empire, where we have really a high computational efficiency, it's not possible to resolve this and simulate it in a nice manner. And the meander element that is located behind a PEC shield wouldn't be a problem. That's doable in Empire and also in HFSS, I guess. But this little detail here inside the HIS structure makes life really complicated in that numerical simulation. That's why we took OpenEMS. As you can imagine, it took a while, but it was doable. And here on the right side, you can see the results concerning B1 plus magnitude over the square root of the accepted overall power. So we calculate the accepted power from each coil and add them up, multiply them by 8 due to the symmetry. Again, we used a cylindrical phantom with the corresponding material parameters. And here you can see the details. The diameter of the phantom was 20 centimeter. The distance between coil and phantom was only 1. And the distance from dipole to HIS shield or the PEC shield was also 1 centimeter. And here I guess you can see that the field here in the phantom is larger for the HIS compared to the conventional PEC shield. What you see also is this broadened area with large V1 plus compared to this more narrow and typical profile that we know from the dipole coils. You may ask, why do you have this hole in the center? It's an issue, let's say, in OpenEMS. The field in the center is not plotted in cylindrical coordinates due to the fact that at the center, along the z-axis, there is no alpha component defined. So it's kind of a field singularity thing. That's why it's not plotted. But Maxwell's equations are evaluated in a proper manner. The EZ component would be at the center, and then the circulation of the magnetic field around is considered. So Maxwell is solved there, but it's just not this. So it's not a big deal. Yeah, so that would be really the final result. Currently, we do also measure. We build it up. And currently we do also measurements with that multi-channel coil. One problem in the MRI scanner is this huge metal ground plane here. Initially, we just make it homogeneous to keep it simple. But before going to the scanner, we either need to make slits in that ground plane and solder big capacitors about the gaps. in order to prevent the problem with the gradient fields. You know, the gradient fields are also normal to that closed loop, and that would cause a large currents that are induced. Another way would be to remove the ground plane and just keep, you know, the top metal layers, but that would involve a redesign of the HIS unit cell. That will be one of the next steps. Yeah, finally, I would like to conclude my talk. I showed to you how we can characterize this HIS structure. There is the reflection phase property. This more or less explains the high impedance surface behavior. You know, when you have the reflection coefficient of +1 instead of -1 for a metal reflector. And the second one would be the dispersion diagram, where I showed you the electromagnetic band gap of the structure. Usually the zero reflection phase frequency is inside this band gap. Then we put this HIS shield behind the dipole, and yeah, I showed to you that we have improvements, a broader V1 plus, and also more penetration depths. The difference is not huge, but at least for the multi-channel arrangement, we could clearly indicate that we get an improved V1 plus magnitude distribution inside the phantom. Yeah, and for the simulators, we use several of them. We use HFSS for the reflection coefficient calculation. We use COMSOL usually for let's say more simple structures where the mesh, where the degrees of freedom in the mesh are not so large, because COMSOL really needs a lot of memory and usually also a lot of simulation time. FDTD is quick and the memory demand is quite low, but there are problems. For example, if you have these tiny substrate layers, and when they are also curved, there are issues, as you can imagine, and as I've shown. But then OpenEMS come to the play with its cylindrical FDTD mesh. Yeah, thanks for your attention, and I'm open for questions.